Good morning, welcome to Quick Programming and welcome to the Solidity Bootcamp. We're going to create a simple smart contract which will basically learn us the basics of the Solidity syntax, how to deploy and compile a smart contract with the Remix IDE, and how to test it. So let's first begin with the Remix IDE. Remix is a open source IDE which has a desktop version and a online version. It's especially made for EVM compatible blockchains. You can connect MetaMask with it if you'd want, but we will always be testing using the JavaScript VM, which is basically a virtual local blockchain which we can deploy contracts to, which we can then test. So we're going to make a advanced version of the storage.sol file, which is a file that will appear when you first boot up Remix. It's just an example smart contract, and we will be creating a advanced version of this one, which will feature all important Solidity features. Okay, so let's get started by creating a new file. The name really doesn't matter. You can call it mycontract.sol. As long as it has the .sol file extension, it should work. Next up, we need to add the license identifier and a Solidity version. We can just copy this for now. It doesn't really matter which version or which license you use, especially for a contract that's just meant for learning the language. But it's useful to know why you should add a license and why you might want to specify a certain Solidity version. Since everything on the blockchain is basically free to view, anyone can view your contracts, its transactions. If you have verified the contract on Etherscan, everyone can just copy your code and they might be able to make a profit from it. That's why you would want a license. You might want to say, yes, you can copy it for just testing purposes, but you cannot use it for commercial purposes. The Solidity version is specified using the pragma Solidity keywords, and after that you can specify the version or versions. I just copied this from the storage.sol file. If you ever want to use newer features of Solidity, you might want to specify a higher version, or if a higher version might break your contract, I don't know, maybe you have copied an old contract from Etherscan, then you might still want to use a lower version. Alright, so let's create a contract. Let's just call it my contract. We use the contract keyword for that. And then you specify a name of the smart contract. This will be the actual name. The file name really does not matter much. I think the file name still is, you can still view the file name when you verify a contract on Etherscan, but the name of the contract in the code is more important. Alright, so let's start by just basically copying storage.sol. We have a uint, which is a unsigned integer with a length of 256. That the length of that specifies how big the integer can be. Then we can give it a name. We can also say that it's public, but since we want to create a getter and a setter, we probably want to make it private. You don't have to specify this, but it's always good to do. So let's just say my number. If you want, you can give it a value already, but again, that's not necessary. It will just give a default value if you try to retrieve the value from it now. In the case of a uint, that's 0. So a function. Let's create a setter because we need to set the value. So let's just call it set. This is the basic syntax of a function. We also need to give it a identifier to see if it's public, private. You also have internal, and you also have external. But for now, public should be fine. It doesn't return anything. It's not a pure function since it will use an outside variable. Yeah, so let's give it a parameter. The parameter is a uint, and I always prepend my parameters with a underscore. So just underscore num. And then we say my number equals underscore num. If we want, we could already deploy this and check how it works. But since we have my number as private, we still need to get or to create a getter. So let's just say function get. We don't have any parameters for this. It will be public. But since we don't alter values, it will be a view function. We only view the data in this function, so it will be a view function. And it returns a value. So we need to also specify what it returns. In this case, it returns a uint 256. And then we just say return my number. And don't forget to end every line with a semicolon. So if we go to the Solidity Compiler tab, we can select the compiler version. The default is fine for now since it's between this. We can click on compile. If there are any errors, it will show them. Down here we can publish it, and we can get compilation details. We can copy the ABI or the bytecode, which is not important for now, but it's useful to know where you can find the ABI for if you ever need it when you want to use it in a D app, for example. Next up, we go to the deploy and transactions tab. By the way, the linter is giving an error, but it's not a compilation error, just a styling error. So we just select the JavaScript VM since it will be local. We can just select the first account, which it makes for us. The gas limit, the value, doesn't matter. The contract, we only have this single contract. We don't implement any other contracts, so we can just deploy the one we have made. It will deploy it if we get the value. It will be the default, which is 0. And if we set it to 222, we can see that the transaction has been confirmed. We can get it again, and the value has been updated. All right, so this is basically storage.sol. It's a very simple explanation it's a very simple way to learn the first basic syntax. Let's see what this says. Does not satisfy the RSM for a requirement. Okay. So this is a very basic contract. And this might be your first smart contract, so congratulations. All right. So next up, we might not want to use or to only have a single value. We might want to have let's say a logbox or a save, which can contain multiple values, which will be indexed. So for that, we can use a mapping. So let's see, mapping. Let's think about this. A uint 256 that will return a string. I like that. My numbers. All right, let's see if this compiles. Nope, I messed up the syntax probably. Expected the equals. All right. So this should compile. Yeah, my number doesn't exist. So this will be my numbers, square brackets, we should give it an index. So let's say underscore index, underscore index is the number we specify. The getter should also get an index, which is a uint256. And then we can say my numbers underscore index. So let's see. Oops. Had a comment too much. String storage. My bad. Alright, so let's talk about strings for a little bit. Whenever you use a string in a parameter, you need to specify its memory. You need to specify this. So it's not only string underscore num. It's not only string word, but it's string memory. You can also use string call data, but for when you're learning, you can basically always use memory. You can Google what call data will do, but string memory will almost always be fine. Let's see, and it will return a string memory. And it now compiles. Okay, so a quick recap. What have we done since I was a bit fast maybe? Instead of a single number, we have created a mapping, which is basically a sort of associative array. We enter a uint, which in this case might be an index if you want to, but it can be everything. You can have, for example, you can first enter the value for index 0, and after that you don't have to enter index 1, but you can also enter, I don't know, index 200. It doesn't matter. But whenever you enter that index to change or to get the value, it will return the string that's associated to that integer. And let's also call this my words. Oops. So instead of only retrieving a single value, a single digit, we will get a word that's specified per or with a index. And we have altered all the code to use the mapping. We've also used the string memory keywords. So let's compile it again. Let's deploy it, since we still only have a single contract here. Let's see. If we try to get anything, we get an error. Invalid number string. Big number string. So it wants us to give a number. So let's see. 0 is a empty string, which is correct, of course. So if we say this is hello, it will set the value, and once we get the same index, it will give us hello. So this is how a mapping works. But maybe this smart contract is private. Maybe we only want the owner of the contract to be able to change the values. Maybe everyone can retrieve the values, but only we can set them. We can do this in a couple ways. The most easy way is to use a address variable. So we have the keyword address. Let's say it's the owner, and we copy the first account, which is the one we deploy the smart contract with. We just copy it by clicking here, and we just paste it as the value of address owner. Let's say public. You could also say this is private, but if people decompile your contract, they can still see the initial value. You can also create a setter function for it, but we will not bother since we will do it in another way in a few minutes. Okay. So in the setter, we can now say if the person who sends the transaction is the owner, then we will change it. Otherwise, we will not do anything. We won't do anything. So, if the message.sender, the message variable is one that will always be given once you set a transaction, which has a sender is equal to the owner, then we will change it. So let's try this. This compiles. We only have added this if statement and this variable. So we will compile or deploy the contract from the first user. That's easier to understand. So if we get 0, it's nothing. If we can get the owner address because it's public. So we can set the first value to be hello. Now if we get it again, it's hello. But if we change the account to the second one, we can be we could try to alter the first value with index 0 to be blah blah. We can send a transaction, it's still confirmed, but if we get it again, it hasn't changed because it is the message.sender, the person that sends a transaction, is not equal to the owner, so it will not do this part. Okay. So the next thing, instead of having our owner address publicly right here, we can set it in a much better way. We can add a constructor. We can just say private owner, so we don't set anything. And then we can say owner equals message.sender, because the only person or the sender that can call the constructor will only be called once when you create the smart contract, when you first deploy it. And it's only called by the person that deploys the contract. So for testing purposes, let's keep it public. The owner variable. We will, again, select the first one, which is 05B3. Let's try to remember that. Then we can check the owner, and it's 5B3. So because we have deployed the contract, we have entered the constructor, and the message.sender is the person that has deployed the contract. So now we, as owner, can simply say we add a value. But if we switch to the other account, AB8, those values might differ for you, by the way, the account hashes. But now we can try to say, let's alter it, but it won't change. I have messed something up, but okay. So that's how we use the constructor, which is another new thing that we have now learned. So next up, we can make it even better. Since this, we might have a smart contract with 20 functions, out of which 10 functions should only be able to be called from the owner. And we might want to also fill the transaction if it's not the owner. to save gas for the users if they ever try to call the wrong functions. So we now have this set, right? We now automatically get the owner address from the constructor. So if we ever deploy this smart contract with another account, the owner will always be the right one. So we don't have to worry about what's behind here. Yeah, let's keep it public, shall we? If you want, by the way, you could also say something like this. You could add the parameter owner to the constructor, and then let's see if we compile this. Underscore owner. If we compile this, we now have a little owner variable that we have to fill before we can deploy it. Yeah. So we have a little field here in which you can copy paste the owner address and it will again work. This might be useful if you don't want the deployer to be the same as the owner. But we will not do that. Message sender. Right. Okay. So again, we might have a very long smart contract with 20 functions, out of which 10 will need to only be callable by the owner. And we want to fill the transaction if it's not the owner. So let's talk about the second thing first. Failing a transaction if it's the wrong person. For that we have the require keyword. Require. So this means it's required that message.sender is equal to the owner. And if you want, you can also give a error message. Caller is not owner. Let's see how this works. So we have compiled the smart contract with our second account. It looks like we have compiled it, but we didn't deploy it yet. But yeah, we have deployed it now with our second address, which is the AB8 one. Okay. So we can set a value. We can get a value, which is the one we have just set. But if we change to another address and we try to set it, it will append and it will fill the transaction, which you can see right here. The transaction has been reverted, which means it cannot be completed, so it just goes to the previous state. The reason provided by the contract is what we have specified right here. Because the caller was not the owner, it will fill and give this error message. This is obviously very useful to know, because you can now better test your contract. You know, if you see, oh, the smart contract fails because of a require statement, if you give a reason, anyone can just see, oh, that's why it failed. So instead of thinking that the problem lies with them, it might be that a hash was generated incorrectly from a server or anything like that. So they have a better understanding of what went wrong. If you want, you can also have multiple require statements, but I will not do that here. And we will change it to fix the next issue that you might encounter. Just imagine our smart contract is very, very long right now. It's billions of functions, and we only want a few to be able to be called by anyone. That's where modifiers come in. A modifier is something that we can add to a function. So we can say public only owner. Aha. Since we don't have a parameter here, we can just omit the parentheses. But if you want, you can also say something like this. And then you can just add your reason right here, which is again useful for providing better error messages. But since the error will always be the same for only owner, which is this line, which we have just made, it will always give a proper explanation as to why the transaction failed. So we have now public only owner, which is the modifier which we have created, which requires the sender to be the owner. Otherwise, it will give an error saying that the caller is not the owner. If it passes through that require statement, we want to say underscore. The underscore will mean that it will return to the normal flow of things. So it will check this, and afterwards, because of the underscore, it will continue with the set function. So again, let's check this. We compile the contract. We delete our previous contract. We select our first user. We deploy it. We can check who is the owner. Well, it's 5b3, the address that we have selected. We can set a value. We can, of course, get the value. Oops, but if we change to another user, so 03C, which is not the owner, and we try to send a transaction, it will be again reverted because the caller is not the owner, which is now not specified within the set function, but in our modifier. Yeah? Okay. So again, a quick recap of what we have done so far. We have basically made a more advanced storage.sol smart contract. We have a mapping of words that are linked together with a number. So 0, 20, 51 can all be different words which we can set and which we can retrieve using the set and get functions. The set function is, although it is public, it is only accessible by the owner because of the modifier that we have created. And we know who the owner is because we set a owner variable in our constructor, which is linked to this owner variable right here. Okay, so then there is a final thing that I want to show you, which is a event. Sometimes you might want to have events. You might want to say, all right, this is, or whenever this happens, I want to be able to catch that from a server, for example. You might want to have a Raspberry Pi with a screen that says a new token has been minted, a new change has been made, or in our case, a word has been set or changed. So we say event, word changed, which is very simple. Oops, let's see if it's correct. That's what I thought. So it appears to be with parentheses. All right, event word changed. We could give it some parameters if we want. And here we say emit word changed. Again, parentheses, yep. So every time we change a word, it will emit an event, the word changed event. So let's deploy the contract and let's set a new value. The word is now numbers, but it's still a string. So this latest transaction is the one we just sent. Setting a new value. So we can open this up, and we have the status. It's true, it's mined, it's executed. We have a transaction hash from the address that we are to the contract that we use. That is deployed to this address, which you can copy here, and then you can see that right there. The gas that we used, the input decoded, the output, and the logs. And within these logs that you can catch from a JavaScript application, a server, or anything, it will have event. You can also emit multiple events. But in this case, the event that's been emitted is word changed, because we have changed a word since we have set a new word. And then we have the value. So that is it. This is the absolute basics of Solidity. We have now created a very simple smart contract which uses almost all of the features that most smart contracts will use. We have functions, we have modifiers, events, we use the constructor, and we have some variables. So let me end this off with a final note. First of all, if you have watched the whole thing so far, thank you so much. It is my first tutorial that's like this, and I hope it helped someone, because I know I'm a bit like all over the place and a bit fast maybe, but I hope that it did help someone understanding what Solidity is capable of and what certain things do. So the final thing I want to say is we might want people to have to pay to set a word. Then we would obviously remove only owner. But since paying for transactions, stuff like minting NFTs, is a pretty common use, I will try to explain it. We have already taken a look at the message keyword. And in this case, we have only checked message.sender. But there's also, let's see. There's also another keyword, which is message.value. So let's say message.value should be more than 1 ether. And again, ether here is another keyword, which makes it easier, because otherwise you would have to add 18 zeros. So the value should be more than 1 ether. Let's see if this compiles. No, I think it will complain about ether. Of course. Function public payable. That's it. Yep. We need to say that the function is payable. This will make sure that you can add a value to the message. So the message should be more than 1 ether, which of course it is absurd for most things. I mean, probably Bored Ape Yacht Club can do something like that. Let's deploy this contract again. Oops. I didn't want to publish it to IPFS, but okay. Now you can see that the set button is red, which means it's a payable function. So we want to say on index 0 add ASD. but it will fail and it will say not enough ether, which is the error we have set here. That's because message.value is 0. We haven't entered anything, and we want it to be more than 1 ether. So how do you set the value to a transaction using Remix? If you scroll a bit up, we have value right here. You can set this to ether. A Finny is like 1,000, then a millionth, and so on. So we say, because we have more than, we can set it to 2 ether, which is more than 1 ether. All right. And then, because we have set the value now to 2 ether, we can send the transaction again, and you can see that it has been completed. Because we have set that value of 2 ether. Let's see, it's a bit glitchy right now. The logs, oh my god. Yes, all right. So over here we have the value again in inside the transaction logs, which we have opened from here. We have value which is this much way, which is 2 ether. And again, you can see why the ether keyword comes in handy. So, yeah, this is the absolute basics of Solidity. You can now, in theory, implement the whole NFT standard by yourself. But you can also, if you want, look up OpenZeppelin and see how you can continue learning by using other people's contract, which you can implement and which you can override functions and all that fun stuff. So again, if you have watched this whole thing, thank you so much. If you want, you can give me a like, give some comments, give me feedback, please, because I really want to know everything that I can do better. I know I was all over the place, but I still hope that you have learned something. So, have a good day. Bye-bye.